All right, in this video, we're going to introduce binomial probability distributions. We're going to look at calculating probabilities of binomial distributions. So what the heck are those things? Well, a binomial probability experiment is an experiment with the following conditions. So we have a fixed number of n repeated independent trials. So we are not going to change how many trials we have, and the trials will be independent of each other. Each trial's outcome is either a success or a failure. So it's either yes or a no, true or a false, success or a failure. And failure just means the outcome did not happen. So it doesn't necessarily mean that's bad. It just means the outcome did not happen. And success means that it does. So the probability of success, which we use a letter P for here, also never changes. So we don't have to worry about, maybe having a 1 in 3 chance on this trial for a binomial experiment, but in the next one having a 1 in 4 chance within the same repeated number of trials. So for instance, we have the number of heads when flipping a coin 3 times is a binomial experiment. First of all, if we kind of run down the bullet points here, we do have a fixed number of n repeated independent trials. So we are flipping the coin 3 times, and each outcome is independent of the one before it. So fixed number of times, each of the outcomes are independent. Each trial's outcome is either success or failure. So we either got the coin to show up on heads or the coin to show up on tails. So in this case, success means that the coin flip resulted in heads. Failure means that the coin flip resulted in tails. And also the probability of success never changes. The probability of flipping heads each time is always going to be 1/2. So it is a binomial probability experiment. So another thing to consider is that as far as this experiment is concerned, in the outcome for 2 heads, heads, tails, heads, and tails, heads are all considered to be equal. So flipping a coin and having it land on heads twice, it doesn't matter what order the heads showed up. So in this case, it doesn't matter what order. We've talked about that in the speed counting section when we looked at combinations. So combinations are going to play a role in binomial probability distributions and the formula for binomial probability distributions. So also note that if 2 heads are obtained when flipping a coin 3 times, then the remaining flip, one more flip in this case, because we flipped it twice, must be tails. So whether the tails is at the end, in the middle, the beginning in this list of outcomes here, the total number of times we flip a coin minus the number of successes has to equal the number of failures. So heads also has a probability of 1/2 of occurring. Tails has a probability of 1 minus 1/2, which also happens to be 1/2 of occurring as well. So the probability of success is, in this case, 1/2. To calculate the probability of failure, take 1 minus that probability of success. So it's the complement rule from our probability involving the word or. So combining the idea of combinations, where it doesn't matter what order the outcomes were attained in, the number of successes of each event, and the probability of success and failure, we get the following formula for calculating probabilities for binomial distributions. So we have probability of x equals x, so lowercase x, remember, represents 0, 1, 2, 3, 4, whatever. In this case, they're going to represent successes. So 0 successes, 1 success, 2 success, 3 successes, etc. is going to be equal to, here's our combination with n and x, so that's the heads and tails order doesn't matter. Our probability of success raised to the x power, because we want it to happen x number of times, like 2 times flipping the coin, times the probability of failure, which is 1 minus p, and sometimes courses use a q instead of 1 minus p, so if you see q, it means the same thing, to the power of the total number of trials minus the number of successes. And that's what we talked about up here, where we have 3 times we're flipping the coin, and we want 2 of those 3 times to result in heads. That means this failure here, the flipping tails, would be to the first power, 3 minus 2. So we'd have 2 heads and a tails in some order. So again, it doesn't really matter what order that is. It could be heads, tails, heads, or heads, tails, heads, or heads, heads, tails. They're the same thing. And again, our formula for combinations, n factorial over x factorial times n minus x factorial. All right, so example 1, which is more likely when flipping a coin, obtaining 4 out of 5 tails or obtaining 8 out of 10 tails? Now, what's interesting about this problem is a lot of people might think, well, it doesn't really matter since 8 out of 10 reduces to 4 out of 5. And while, that's true, 8 out of 10 reduces to 4 out of 5, does it guarantee that the probability is going to be the same? So for the 4 out of 5, we have 5 trials, and 4 of them are obtaining tails, so 4 successes. So 5 factorial over 4 factorial times 5 minus 4 factorial times the probability of success is 1/2. That's going to be raised to the 4th power times the probability of failure, which is also 1/2, but that's raised to the 1st power. And note that the exponents, when you add up the exponents, 4 and 1, you get the total number of trials, which in this case is 5. So that should always be the case, where this exponent plus this exponent equals this first value in the front of the factorial here in the binomial formula. So calculating all this, we get about a 15.625% chance that if we flip a coin 5 times, 4 out of those 5 times it's going to result in tails. So now let's see if the 10 or the 8 out of 10 gives us the same answer. And for 8 out of 10, it's going to be 10 factorial over 8 factorial times 10 minus 8 factorial. And then 1/2 to the 8th times 1/2 to the 2nd. And when we calculate this, we do not get the same probability. So the probability actually goes down. And if you think about it, you're having more trials now with 10 versus 5. So even though 4 out of 5 is the same as 8 out of 10, when flipping a coin more times, there's more of a chance that your outcomes are going to go down. So you're not going to get the exact same result, because now you're adding more risk by increasing the number of times you flip the coin from 5 to 10, even though the ratios are the same, 4 out of 5 and 8 out of 10. By flipping it more, you introduce more risk, which lowers the probability of success. So it's more likely that you'll obtain 4. Actually, it's the same. It says tails, heads. It actually would be the same with heads as well. But 4 tails from 5 flips of the coin, then 8 flips of the coin. So I got lucky. The same probability. All right, example 2, a multiple choice test consists of 10 questions with 5 answer choices per question. So maybe like A, B, C, D, E. What is the probability that a student guesses correctly on 6 questions? So let's say they need to get a 60% to pass, and they're trying to calculate what are the chances I get 60% on this by purely guessing alone, which hopefully you are not doing. So probability that we guess exactly 6 questions correct on this multiple choice test, we have 10 factorial over 6 factorial times 10 minus 6 factorial. And then we have the probability of success is 1/5, that you guess correctly is 1/5. You want to get 6 of those right, and then the rest of them would be wrong, which in this case, if there's a 1 out of 5 chance you guess correctly, there's a 4 out of 5 chance that you do not guess correctly. And again, note that 6 plus 4 does give us our total number of questions here, which is 10. So this student has a very small chance, about a little bit more than 0.5% chance of guessing correctly on 6 questions. So, okay, that's a pretty small chance of getting exactly 6 out of 10 correct. But what is the probability that the student gets at least 6 out of 10 questions correctly from guessing alone? So, in this case, getting at least 6 out of 10, if that's If 60% is passing, anything higher than that will also be passing. So let's see what the student's chances of getting 6 out of 10, at least 6 out of 10 questions correctly are. So that means what we could do is we could find the probability of getting 6, which we just did, but then we'd have to add to that getting 7 right, getting 8 right, getting 9 right, and then getting 10 right. Or rather than do that, we can use a cumulative binomial calculation with the complement rule to achieve this as well. So most calculators and technologies not only have the ability to do single event binomial distributions like getting exactly 6 out of 10, they also have cumulative, which goes from 0 up to and including the number before the value of interest here. So in this case, the probability of guessing at least 6 of them, getting 6 or more right, is going to equal 1 minus the probability of getting less than 6 right. So in that calculator, you probably have to put in less than or equal to 5. So 1 minus the probability of 5 or less. And that'll actually come out to be not exactly a whole lot better, but slightly better. So now they're at about a 0.637% chance to pass the test if they need to get 6 out of 10. Now to that, and I'm going to link this in the description, I have a binomial distribution calculator. So if you don't feel like going out and spending a lot of money on a graphing calculator, I'll link this stuff in here. You'll really only have to change really just these 2 items, the number of trials, which we use n in our formula for, and then the probability of success. This is the decimal place that our answers are going to round to, and then everything else in here you can just leave it as it is. So that way all you have to change is the number of trials and the probability of success. So we have 10 questions, and our probability of getting a question right is 0.20. So make sure your probability is between 0 and 1. And then once we run this, it's going to give us a table. And I'll just show you what it looks like here. Okay, so here's our table. And if we go back to our first question, it asks, what is the probability of getting exactly 6 out of 10, which was, let's see, what was exactly, 0.00551. So if we look at down this list, getting exactly 6 out of 10, 0.0055, and then this goes a few more decimal places than that one did. But you can see you get the same answer just from x equaling 6. Now for this one, getting at least 6 out of 10 means probability is 6 or more. If we take a look at the probability of 6 or more, in this last column I have x is greater than or equal to that value. So if we look at the 6 again and just look at this row, the probability that we get 6 or more questions correct is 0.0063. I believe we had it go to 637. So yeah, this one will calculate greater than or equal to, and we'll also calculate in this column less than or equal to. So the probability that a student gets less than or equal to 6 questions right is pretty high, which, if you can imagine, you're guessing on this multiple choice test you didn't study for, you're probably not going to do a very good job on it. So, all right, again, I will link that in the description so you can use it. But that about does it for this video. Thank you for watching. I'll see you next time.